while on the right-hand side, it is chromium 3+. So ion 2 going to ion 3 means that ion is oxidized. So it is the reducing agent. So the half equation for that becomes ion 2 going to ion 3+. As you can see here, unlike the last example we did, this is another way to actually solve or balance the equation. Here, from writing the half equation, we have indicated how many electrons is lost or gained. So ion 2 going to ion 3 means that 1 electron was lost. And that is why we have 1 electron here. And then for the chromates ion going to chromium, chromium gains 3 electrons. As you can see, on the left-hand side, the oxidation number is +6. And then on the right-hand side, the oxidation number is +3. So it is the oxidizing agent. So the half equation for that will be the chromium in the +6 oxidation state. It has gained 3 electrons, so we are adding electrons to this. And then it moves to the right-hand side, chromium in the +3 oxidation state. So, like we'll balance each kind of atom other than hydrogen and oxygen. So we look at the two half equations and see if the atoms are balanced. In the case of ion 2 going to ion 3, there is no imbalance in the ion, so we leave that. And then when we now go to the other one, chromates ion +3 electrons going to the chromium 3+. As you can see on the left-hand side, we have 2 atoms of chromium. That is why we are putting 2 beside the chromium 3+ in order to balance the chromium. The next thing, we'll balance oxygen atoms by using water. The one involving ion 2 to ion 3, there is no oxygen, so we leave that as it is. And then the other half equation, when we look at on the left-hand side, we have 7 oxygen. So on the right-hand side, for each oxygen, we are going to put 1 mole of water. For every atom of oxygen, we put 1 mole of water. So that is why we have 7 moles of water on the right-hand side. The next step, we balance the hydrogen atoms by using hydrogen ions. Now, this chromates +3 electron going to chromium 3 + 7 water. The introduction of 7 moles of water has brought about 14 hydrogen ions. So that is the next thing we shall write, 14 hydrogen ions to balance the number of water on the other side. Then we now use electrons as needed to obtain to make sure that the charge is balanced. The half equation for the oxidized species, Fe2+ going to Fe3, there is nothing to balance there. The number of electrons is balanced. Now, going to the other one. Yeah, so this is showing us how we balance the electrons. Ion 2+ is +2, ion 3+ +3, then electron -1. So it's balanced. 2 on the left-hand side, 3 - 1, 2. And then when we go to the other equation, we have 14 hydrogen ion will give us +14. And then we have 3 electrons, and then -2 is the charge on the chromate ion. So +14 - 2 - 3, that will give us +9. And then on the other side, we have 3 plus times 2. You multiply by the stoichiometry, that will give us +6. And then water has 0. +6 and 0 is 6. So that means this is not balanced. This needs 3 electrons. Add 3 electrons to the reactant side. because that's where you have +9. So you need to subtract 3 to make sure you have +6 on the other side. So when we now add another 3 electrons to the existing 3, it becomes 6. So when we add up all of these, you will realize that we have 14 + 2 + 6. Okay, and then on the other side, we have 6 and 0. So 14 + 2 + 6 give us 6. 14 + 2 - 6 will give us 6. And then 6 + 0 will give us 6. So the charge is now balanced. Now it's time to add up. So we have 6 electrons on the reduced half equation. We have only 1 electron on the oxidized half equation. So we need to multiply this by 6. And then this multiplied by 1. So it's just like exchanging the stoichiometry of the electrons. So now on both equations, we have the same number of electrons. Then we can then add up together. The electrons will cancel out. And so this will now be our final balanced equation after canceling out the number of electrons, the 6 electrons. Always check to make sure that all the atoms and charges are balanced. In this case, they are balanced. So these are practice questions for us to lay our hands on using acidic medium. Now, the next one we want to look at is balancing in basic medium. So, just like we did in the case of acidic medium, we use the half equation until we get to the point where we introduce hydrogen ion. Now, because it is in basic medium, we want to get rid of that hydrogen ion. So we will now add OH- on both sides. So wherever there is hydrogen ion, once you add OH-, it will combine to form water. We shall see in the example that we are going to take. Then we eliminate the number of water molecules that appear in both sides of the equation. And as usual, we check that the elements and charges are balanced. So, for instance, we have this reaction, the iodide ion and the permanganate ion in basic solution to yield iodine and manganate form. So this is the equation of reaction. So just as we normally do, we identify the oxidizing and reducing agents. So the iodide ion is the oxidation half because it is the one that is oxidized, the loss of electron. And then the manganate ion, you have manganate going to MnO2. So we have the MnO4 minus gaining 3 electrons because the oxidation number of manganese in MnO4 minus is +7. And then its oxidation number in MnO2 is +4. So it will gain 3 electrons to become MnO2. That is the reduction half. We continue, we balance all the atoms except hydrogen and oxygen. As we can see here, just a minute. In the oxidation equation, we can see that the iodide is just 1, and then iodine, you have 2 atoms of iodine there. So we need to balance that. 2 iodide to give I2+ electron. And then for the manganate going to MnO2, that's the manganese, only 1 manganese on the left-hand side and only 1 manganese on the left-hand side. So that is balanced. So the next thing is to balance the oxygen by adding water. So we have 4 oxygen on the left-hand side, and then we have 2 oxygen on the right-hand side. So we need to add 2 moles of water. That is why we are having water here to balance the oxygen. The introduction of 2 moles of water has brought about hydrogen atoms. So on the right-hand side, we have 4 hydrogen atoms. So on the left-hand side, we are going to introduce 4 hydrogen ions, as we can see. Now, this looks like what we see in the acidic medium. But because this is a basic medium, we want to eliminate this hydrogen ion. So what we are going to do is that for every hydrogen ion, we'll add 1 mole of hydroxide ion. On the left-hand side, we have 4 moles of hydrogen ion. So we are going to add 4 moles of hydroxide ion on both sides of the equation. So that is the one highlighted in red. That is the hydroxide ion we have added on both sides of the equation. 4 moles of hydrogen ion will make us add 4 moles of hydroxide ion on both sides of the equation. Now, the side where we have the hydrogen ion, which is the left-hand side, the 4 hydrogen ion and 4 hydroxide ion will combine to give 4 moles of water. That is the way we want to eliminate the hydrogen ion, because it is not acidic medium. This is in basic medium. You don't need hydrogen ion. So we now have 4 water in place of 4 OH and 4H. 4 OH and 4H will combine to give 4 water. Okay? Now, if we look at this, we can see 4 moles of water on the left-hand side and 2 moles of water on the right-hand side. We don't need to have them like that. So we subtract where you have the greater moles of water. 4 moles of water minus 2 moles of water will leave us with 2 moles of water on the left-hand side. So that is what we are seeing now. I hope we are following. So the next thing now is to use electrons to balance the charge. So here we have 2 iodide, that is -1 times 2, -2. And then on the right-hand side, iodine is 0, 1 electron is -1. So this is not balanced. So we need to add 1 more electron on the right-hand side to balance the charges. So it now gives us 2 iodide ion plus iodine plus 2 electrons. Now the charge is balanced. Going to the other half. Here, water is 0. The manganese ion is the charge is -1, and then we have 3 electrons. So 0, -1, -3, -4. And then on the right-hand side, MnO2 is 0. Oxide ion, hydroxide ion is -1. -1 times 4, -4. So 0 -4, -4. So in this case, you have -4 on the left-hand side and then -4 on the right-hand side. Here, the charge is balanced. Now we need to add the 2 equations together, making sure the electrons are balanced. As we can see, the first one has 2 electrons. The second equation has 3 electrons. So we exchange. We multiply that by 3 and then multiply the second one by 2 so that we can balance the number of electrons. So what we now have here is 6 iodide ion to 3 iodine plus 6 electrons. We have 4 water plus 2 manganese ion plus 6 electrons to give 2 MnO2 plus 8 hydroxide ion. Now the number of electrons are balanced. We can then add them together by cancelling out the number of electrons. So what we now have is 2 MnO4 minus plus 6 iodide plus 4 water to give 2 MnO2 plus 3 iodine plus 8 hydroxide ion. Always check to make sure that the atoms and charges are balanced. We'll take another example of basic medium. This time around, we have Mn2 plus hydrogen peroxide to give MnO2 plus water. In the same way, we identify the oxidizing and reducing agents. Mn2 plus going to MnO2. That is increase in oxidation number. That is the oxidized species. And then the other one, hydrogen peroxide going to water. Oxygen change from -1 to -2. That is decrease in oxidation number. That is the reduction half. So we have identified the oxidation reaction. We have identified the reduction reaction. The next thing, just like we do, we'll check that the number of atoms are balanced. So when we check manganese on both sides, there's only one Mn2 plus on the left-hand side, and then only one on the right-hand side. So that is balanced. Now, the next thing is that we balance the oxygen by using water. When we check this hydrogen peroxide plus electron going to water, we can see that there are 2 atoms of oxygen on the left-hand side and only 1 atom of oxygen on the right-hand side. So we add 1 more mole of water on the right-hand side. Oh, okay, sorry. Before we get to that one, let's check for the first one, the manganese and manganese. In the manganese 2 plus and MnO2, we have 2 moles of oxygen on the right-hand side and nothing on the left-hand side. So that will make us add 1 mole of water. And then for the hydrogen peroxide, we have 2 oxygen atoms on the left-hand side and 1 oxygen atom on the right-hand side. So that will make us add another mole of water to the right-hand side. That's why we are now having 2 moles of water on the right-hand side. So the next thing, once we introduce water, we introduce hydrogen. So we need to balance the hydrogen atoms. For the oxidation half, we have 4 moles of hydrogen on the left-hand side, 4 moles of hydrogen atoms on the left-hand side, and nothing on the right-hand side. So we need to add 4 hydrogen ions. And then for the hydrogen peroxide, we have 4 moles of hydrogen ion on the right-hand side and 2 moles of hydrogen atoms on the left-hand side. So we need to add 2 moles of hydrogen ion on the left-hand side as well to balance the hydrogen. Now we have gotten to the stage where we need to add OH minus. So for every hydrogen ion, we need to add the equivalent number of OH minus on both sides of the equation. So the first equation, we have 4 moles of hydrogen ion. So we are going to add 4 moles of hydroxide ion on both sides of the equation. That's what we can see highlighted in red. And then for the second equation, we have 2 moles of hydrogen ion on the left side. So we are going to add 2 moles of hydroxide ion on both sides of the equation. Okay, so the addition of OH minus here will combine 4 OH plus and 4 OH minus. We combine to give 4 water. That is why we are saying 4 moles of water on the right hand side. And then we have 2 moles of water on the left hand side. So we need to subtract. We don't need to have water appearing on both sides. So we can subtract 4 minus 2 to give us only 2 moles of water on the right hand side. So for the other equation, we also add 2 moles of hydroxide ion on both sides. Okay. So the next thing is to make sure that our charge is balanced. If we look at the Mn2 plus 4OH minus plus MnO2 plus 2 electron plus 2 water, the charge on Mn is +2. The charge on hydroxyl ion -1 times 4, -4, plus 2 minus 4, that will give us a total of -2 on the left hand side. And then on the right hand side, MnO2 has no charge, 0. 2 electrons, -2. Water has no charge, 0. So when we add up this, we get -2. So it means that so we have 0, -2, and 0. So it means that the charge is balanced. So here on the Mn2 plus 4OH minus -4 will give us -2. MnO2 0, 2 electrons, -2, water 0. So here the charge is balanced. But when we look at the hydrogen peroxide plus electron going to 2 hydroxide ion, hydrogen peroxide is 0, electron is -1. That is -1 on the left hand side. And then on the right hand side, we have OH, 2OH minus, 2 times -1, that is -2. So it means there is imbalance on this. So we need to add electron to the left hand side to balance the charge. So adding another electron makes this become 2 electrons, okay? Now, we need to look at the 2 half equations now to make sure that the number of electrons is balanced. If we look at Mn2 plus 4OH minus to give MnO2 plus 2 electrons, we have already said that is balanced. And then there are 2 electrons. And then hydrogen peroxide plus 2 electrons to give 2OH minus. This also has 2 electrons. So we can add up the 2 equations because they have the same number of electrons. So when we add up and cancel out the number of electrons and also the OH minus, you can see that for the first equation, there are 4 OH minus. And then for the second equation, there are 2 OH minus. So we can subtract 4 minus 2 will give us 2. That is why we are seeing 2 OH minus in the final equation. We have subtracted 4 OH minus minus 2 OH minus. That is why we are seeing that in the balanced, in the final equation. So that is how we balance in basic medium. Let me check the chat box to make sure I don't have. If you have any question before we take an example on calculation, we are going to take an example now on redox calculation. So I've given 2 examples already, and I'm adding practice question. So you can use the practice question to lay your hands on the practice question to have a better grasp of how it is done. So basically, it is the same principle up to when you have hydrogen ion. It is when you get to that stage where you have the hydrogen ion that you now introduce hydroxide ion on both sides of the equation. And then you will now, the introduction of hydroxide ion, we form water, and then you now cancel out the number of water. Make sure charges are balanced, and then you add up. It's as simple as that. So moving forward, so these are questions for you to practice. Write balanced equation to represent the following reactions in a basic medium. So these are examples for you to practice. So we want to take an example. A piece of iron wire weighing 0.1568 is converted to iron 2, and it requires 26.4 ml of KMnO4 solution for its titration. What is the molarity of the KMnO4? The first thing is that we write the balanced equation. And I think this is one of the ones we treated earlier. So you write the balanced equation, and then we now use the stoichiometry. It is iron and manganese, between iron and manganese, okay? So we are asked what is the molarity of the KMnO. From the balanced equation, 5 moles of iron 2 will react with 1 mole of the permanganate. This MnO4 minus, if we remove that minus, that is where we have the KMnO4, okay? So how do we know the number of moles of the iron? Is mass over molar mass. We'll be given the mass at 0.1568, and the molar mass of iron is about 56. So when we divide 0.1568 by 56, we'll get the number of moles of iron as 0.002808. Now, this number of moles of iron is what we now convert to number of moles of permanganate. Okay? From the balanced equation, 5 moles of iron requires 1 mole of the permanganate. So it means 1 mole of the permanganate will be divided by 5, the number of moles of iron divided by 5, because the ratio is 5 to 1. So we need to divide that value by 5, and that gave us 0.005616 moles. And we know, of course, our molarity is number of moles divided by volume. So we are given the volume as 26.24 cm3. So we convert that to dm³ by dividing by 1000. And that gave us, when we press our calculator, we have 0.0214 molar. Yes, somebody is putting up his hand. I'm on mute. So do you have a question for me? Yes, ask your question. But you must be in a quiet place so that I can hear you.
Good morning, ma'am. In the question.
Yes.
In the question, it was said that a piece of iron. But
yes.
Ma?
Yes, I'm listening to you.
In the question, it was said that a piece of iron, and iron is Fe, is converted into iron 2. Iron 2 plus. In the equation we are writing, we are converting iron 2 plus into iron 3 plus.
What happened is that iron, that piece of iron, so I'll mute now so that I don't want those background noise. So I'll answer the question. The piece of iron was oxidized, was put in an acid to convert it to iron 2. So that iron 2 was now reacted with the KMnO4. When iron 2 now reacts with KMnO4, that is why we get iron 3 on the other side of the equation. So that iron is a metal ion that was reacted with acid to get iron 2. So it is the iron 2 that now reacts with the KMnO4 to give us iron 3. So that mass of the iron that we are given was totally converted to ion 2. That is why we are converting here number of moles of ion, mass over molar mass, to give us the number of moles. So that number of moles of ion is the same as number of moles of ion 2, because it is the ion that was converted to ion 2 before we now reacted with AMNO4. I hope that is clear.
Yes, ma'am.
Okay, thank you. So the next thing we are going to look at. Oh, okay. There are practice questions here. That is for you to take home. Okay. You have the equation of reaction, and we are asked to calculate the molarity of one of the reactants. Yes, somebody raised hand. We have attended to this question, right? Put down your hand if I have attended to your question already. Or you can put your question in the chat box if that is the case. Somebody is asking, why is K removed in the equation? It doesn't matter. We are just trying to show, because the potassium, what is the active ingredient? Is the MnO4 minus. The potassium does not change oxidation number. That's why we don't bother to put it. So it's not as if we are angry with the potassium. Now, the other type of reaction we are going to look at is decomposition reaction. When we say decompose, it means to break down. So for instance, we have sodium chloride, and we can break it down into its constituent atoms, Na and Cl. In general, when you have a compound, AB, and you decompose it, it means that you are breaking it down into its constituent atoms. So AB broken down into A and B. We have, so that is the compound. We are breaking it down into its constituent elements. So mercury oxide, for instance, look at what it looks like in the test tube. When you apply heat, you break it into the constituent elements. Mercury itself in the liquid, as we can see in the picture, and then oxygen gas. Those are examples of decomposition reaction. Other examples of decomposition reaction, you can have water being broken down into hydrogen and oxygen gas. We could have calcium carbonate being broken down into calcium oxide and CO2. You could have potassium chlorate being broken down into KCl and oxygen. Now, the other type, or the last type of reaction we'll be talking about, is what we call the displacement reaction. So what this is trying to tell us, or what this is all about, if you look at what we have in the picture, we have lithium metal and water to form lithium hydroxide and hydrogen. So in the product, what happened? The lithium metal is replacing the hydrogen. So that is why hydrogen is up. It's like displacing hydrogen from the water. So you have lithium metal plus water to give lithium hydroxide plus hydrogen. So that hydrogen that is standing by itself, or the hydrogen gas, has been displaced. So we call this a single displacement or single replacement reaction, okay? Because only one element was replaced. We'll see examples where two elements are replaced. So that's one we call a double replacement reaction. So other examples of single replacement reaction, when you have zinc metal reacting with HCl. So this is the zinc is going to displace hydrogen to give us zinc chloride plus hydrogen gas. And then we balance it. Also, if you have sodium chloride plus fluorine, we have sodium fluoride plus chlorine. So here, fluorine is displacing chlorine. Fluorine is taking the place of chlorine. That's why you have sodium fluoride and chlorine gas giving up. And then you make sure it's balanced. Also, if you have aluminum solid plus copper nitrate, copper is being displaced while aluminum combines with the nitrate ion. And then we make sure the equation is balanced. Now, double displacements. For example, we have magnesium oxide plus calcium sulfide. So this is magnesium oxide, magnesium and oxygen. We have calcium and sulfur. And then forming magnesium sulfide. You can see here, oxygen went off, sulfur came to replace it. And then in the calcium sulfide, sulfur went, oxygen came to replace it. So this is an example of a double displacement reaction. So in general, if we have AB plus CD, how do we know if it is a double displacement? B will go to C and D will come to A. Okay, so two elements are being moved. So that is double displacement reaction. So these are examples. Oh, okay, we can, okay, think about foiling in algebra. First and outer ions go together, inside ions go together. So that, I think that is one very funny way of trying to remember how these combine. So silver nitrate plus sodium chloride. So silver is outside, is outer, chlorine is outer. So silver and chlorine will combine. NO3 is inner. Sodium is also inner. So sodium and NO3 will combine. Inner, inner, outer, outer. Okay? So to give us silver chloride plus sodium nitrate. Another example, K2SO4 plus barium nitrate. So inner, inner, barium and sulfate are the inner, they will combine. Potassium and nitrate, they are the outer, outer. So they will also combine, making sure that the equation is balanced. Oh, okay, this is actually trying to show us how they combine. Inner, inner, outer, outer. Okay. So we have practice questions here for us to predict the products that will be formed if we have this series of equations. So this is practice question for you. And that brings us to the end of the class. If we have any question in the next few minutes that is remaining, I will attend to your question. So if you have any question, put it in the chat box. Let me see the question and then we'll attend to it. Otherwise, I have come to the end of my class. So I'll go through the chat box to see if there are questions waiting for me. Can we get the slide, man? The slide has been sent to your class rep. So please, Dr. Shuaib has forwarded the slide to the class rep. Meet with your class rep to get your the following algebra. Once it's a displacement reaction, it applies. If you are told that this is a displacement reaction and it's a double displacement reaction, then you can use that following algebra to solve it or to know which and which we combine. The common ones are the ones with two reactants for double displacement reaction. The commonly, one of their attributes is usually that they have two reactants. When is the test? It will be announced to you. So early next year when you resume, we shall have the test of all the lectures you have been taught so far. It will be announced to you. So I think, how many lecturers have taken you so far now? I think 5 people have taken, is it 5 or 6? Yeah, 6 lecturers have taken, 5 lecturers have taken so far. So the tests will be based on all the lectures that you have taken so far. But the date will be announced to you. Oh, yeah, I can see a hand raised up. Does anybody still have any question before we call it a day? I've allowed you to unmute yourself if the person that was raising his hand, if you have any questions. So in the absence of any question, I wish you a happy holiday and see you next year by God's grace. Do take care and enjoy the rest of the day.